Hello, I am Jingguo and I will be presenting my final project with the topic coded aperture. We start by revisiting this imaging model shown in the image. For the thin lens system with a focal length d, if an object is on the focal plane, all its emanating light will focus on a single point in the image plane. If now we move the object to a new distance dk, the object is now out of focus, and the light emanating from it will intersect the image plane in the region of a circle, which is known as the circle of confusion. The image formed by off-focus objects can be modeled as a convolution between the kernel fk and the sharp image x, where the kernel is dependent on shape of the aperture and the distance k from the lens. Changing k often leads to the same kernel but scaled with different values. This image is an example of applying blurred kernels with different scales to an image. We observe that with normal aperture on the bottom, we observe significant artifacts with a larger scale, but it is hard to distinguish between the correct scale and the smaller scale. But with the coded aperture on the top, the difference between the correct scale and the smaller scale also becomes distinguishable, and that is why we want to use coded aperture. The question now arises, how do we tell if a coded aperture pattern is good at distinguishing depths? Say we have an image distribution pk1 of y at distance k1 and another pk2 of y at distance k2. The intuition here is that we want to make pk1 and pk2 as different as possible, so it will be easy to differentiate with using image y. Mathematically, we have the Kullback-Leibler divergence here, which describes this difference, and in the frequency domain, it can be reduced to the equation below, where sigma denotes the diagonal entries of the covariance matrix, and then transformed into the frequency domain. Anyway, the key point here is that we now have a way to measure how good a pattern is. Levin et al. Conducted a random search over a 13 by 13 square millimeter grid with 1 millimeter holes, and found this pattern with a high KL divergence. And this is also what I implemented for my own coded aperture. The lens in my hand has a diameter of 21 millimeters, but I only used the center 11 by 11 square millimeter for the pattern, because we want to avoid radial distortion in the peripheral regions as much as possible. Then we want to get the blurring kernel for the filter at different distances in order to do the deconvolution in the next step. We can do this calibration by first taking a sharp photo of this random curve I drew without using the coded aperture. Then, with the focal length and aperture size fixed, we incrementally increase the distance between the drawing and the camera. For each distance, we first align the sharp photo with the coded aperture with the blurred one, and get the blur kernel by solving an overconstrained linear system. Then we go to deblurring. What I used was the Wiener deconvolution introduced in the lecture, or Levin et al. Also offers another way to deblur, with a Gaussian prior on the image, assuming that the derivatives in a sharp image will follow a Gaussian distribution with zero mean. And then we can get the deblurred image x star by solving this optimization problem. Here CFK is the matrix representation of a kernel Fk, and CFKx minus y is simply the reconstruction error. The other two terms are regularization terms that keep the image smooth. Here we have a deconvolved image using Wiener deconvolution. You can notice here that the ring artifacts that we expect to observe, which means that we are deblurring using a wrong scale. Finally, we can calculate the reconstruction error for each pixel for each kernel. And we can take the sum or average over a pixel's neighborhood and compute this energy. Then we can get the correct depth by choosing the one with the smallest energy E. We can also recover an all-in-focus image by selecting pixels from deconvolved images with the correct depth. Finally, we present the result from running this algorithm. This is an input image taken from Levin et al. Paper with its corresponding filter weights. The left image is the all-in-focus image, and on the top right is the depth map, and on the bottom right it is the image taken with the coded aperture. We see that while the depth map captures parts of the depth information, there are still a lot of artifacts in the depth map which further causes artifacts in the all-in-focus image. For regions such as the wall or the black region in the image, it might not be possible to recover a correct depth map because the surface is not textured. But if we focus on a region on the cups, we can observe some misclassified regions where the depth map should be black, but it is classified as gray. The resulting artifacts in the all-in focus image are also very obvious. The reason for this artifact, I think, is the lambda coefficient term when we're doing the depth evaluation. Levin et al. States in their article that those parameters are learned using a machine learning algorithm on an image data set with known depth information. Neither is this part discussed in the paper, nor do they provide any data on it. So what I can do is I set them all to be 1, which highly likely will cause misclassification problems. And secondly, my deblurring method is different from what Levin et al. Used, but I don't think this will make a large impact on the result. That's all from my presentation, and thank you.